For this problem, we're given the voltage source in Vrms, and we are given our V naught in Vrms. We need to find the average and reactive power for the voltage at V of G. So we're not going to be looking at V naught too much. What we are going to be looking at is our VG. But to use the formula that is provided in the notes linked below the like button, we see that our Vrms is equal to our Vmax divided by the square root of 2. So if we want to find our Vmax, we're just going to have 160 times the square root of 2 equal to that Vmax. So our Vmax is going to be approximately 226. Now what we need to do is find our Imax. So we know in our Imax from Ohm's law is going to be equal to the voltage max divided by the total impedance, or Z T of H. We can just write it like that. Now we know our Vmax. I don't know why I made that an R. That should be an M, but it's going to be 226, and this is all over the ZT of H. To find the ZT of H, we're going to plug it into a calculator, and the calculator is going to look just like this. So we can see that our 15 ohms and the J20 ohm resistor and inductor are in a series with each other. That's why they're being added together right here. However, it's in parallel with the negative J25 ohm capacitor. And so that means it's going to be in the parallel formula, which is this. And all of this is in series with the 2.5 ohm resistor to the left. So we are just adding this here. In doing that, we are going to get 40 negative 12.5 I for our impedance. After writing this in our Imax, plug it back into the calculator right here, and that is going to give us approximately 5.15 plus an imaginary number of 1.61 J. If you're confused on the I's and the J's, I just use I's as placeholders for J, but they're equivalent to each other. We need this in the polar form, so we're going to convert this. In the notes linked below the like button, you can find that the conversion is that our Imax is equal to a Vmax, so we could write this as Vmax is equal to Imax, or if we were finding impedance for that matter, it would be equal to Zmax is equal to the square root of our number squared plus the imaginary number squared, and then we're going to have that our angle is equal to tangent -1 of our imaginary number over our real number. And this is going to give us that our Imax is equal to approximately 5.4 with an angle of approximately 17.3 degrees. If we check our angle, the x is the real number, I is the imaginary number in the y-axis, so that means this is the quadrant our degree should be in, which it is. So that checks out, and we found our Imax. Now what we can do is use this P and Q with this S and find our S of G. Now we can see that there is a plus minus out front here, and that is because the absorption or delivery depends. And what it depends on is if the voltage drop is in the same direction as our current. However, usually a source is supplying power. So this VG right here is supplying power. It's going this way, voltage drop. And when a source typically is supplying power, the current is in the direction of our voltage rise. So the current is going this way, meaning that we are going to have a negative. So when we solve for this, we are going to have that our S is equal to a negative. We are then going to have our P in here, and I'll do it as a big bracket because it's going to be pretty big. We are going to have our Vmax, which is 226, being multiplied by our Imax, which is 5.4 divided by 2, multiplied by the cosine of the angle over voltage. Angle over voltage is 0, so we're just going to have a negative 17.3, which is the angle of our current. And then we are going to have a plus J times our Q. Our Q is going to be very similar, 226 times 5.4 divided by 2, and then we're multiplying this by the sine of the angle of our voltage, which again is 0, minus 17.3 degrees, which is the angle of our current. So we can shove all this into a calculator and see what we get. We're going to get that our S is equal to a negative, out front, bracket 582 approximately, minus J times 182. That means that our S of G is going to be equal to approximately negative 582, and our J is going to be 182. And that is how you go about solving this problem. But to use the formulas that are provided in the